this second interval, that would be basically it would be the midpoint velocity from 0 to 1, right at the half-second interval. We have the average velocity, number 1, and notice that delta t here is 1 second. So we multiply that by 1 second, we multiply it by 1, which is just 1. So the distance traveled in the first second is the average velocity during that second. I'll call it average velocity number 1 times 1, and it will be that many meters. So that would be so the distance traveled right during this interval right here is little delta, is delta d1, okay? And what we do is we add up all the little delta d's all throughout here. So basically what we can say is that the total distance traveled, I'll call big D, is basically the summation of I equals 1 to 20-second intervals of the average velocity times delta t, where delta t is actually 1 second. And what this ends up being numerically is simply the sum of the average velocities 1 plus the average velocity during number 2 plus all the way up to the average velocity in second number 20, and it's equal to that many meters. So that would be the total distance traveled throughout this entire graph. Okay, at this point we've gone through all of the questions, and what I'm going to do now is I'm going to briefly describe the laboratory. In this laboratory, which you all should have a handout of, let's see, here we go. It's a 2.2, well, there's three pages, and notice the third page is an example graph of what I want your data to actually look like. But basically, what is this lab all about? The lab is about measuring the velocity of a ball. You start out with a stopwatch. You have a ball, and then you have a ramp. Your ramp can either be a table or a sloped table, or like a piece of wood. Notice, a piece of wood. Or in this case, I'll also use just a piece of molding with a little bit of, there's a little bit of groove in here. Works quite nicely. And what I do is I measure off 20 centimeters. Actually, the lab gives you directions. You start with, if this is 0, you take your meter stick. Whoops. Take your meter stick and you mark off 20 centimeters from here. That's not exactly 20 centimeters, but let's suppose this is, you mark off 20 centimeters, 40 centimeters, 60, 80, 100. We fix the slope. Fix it like on the floor and prop it up with some blocks. It doesn't really, I don't really care what the slope is. Don't make it too steep. If you make it too steep, you won't, the ball travels so quickly, you won't get an accurate measurement of the time. On the other hand, don't make it too slow, because then you don't want the ball to just not do anything or not roll very much because the slope is too low. So give it a moderate slope. And when you, what I want you to do is this. You follow the directions. You start the ball always at the same point, at the 0 position. and the ball, you measure the time it takes to get to the first point. For instance, here's the slope. Oops. I start the ball at x equals 0, and I mark off 20 centimeters. Oops, 20 centimeters. Then I mark off 40 centimeters, 60, and so on, all the way up to 100. I take my stopwatch and I measure. I start it here and I let it roll down to here, and I don't stop it. I let it roll past. I don't want to stop it, but I'm going to measure the length of time it takes to start it, for it to pass here. I'm going to do that 10 times. So for this measurement here, I'm going to get 10 measurements, T1, T2, all the way to T10. I'm going to get 10 measurements of the length of time it takes from the ball to roll from here to here. I just let it roll on through. I don't try to stop it. I don't try to stop the ball. Then I do the same thing. I do 10 measurements from here down to here, T1 all the way to T10. Likewise, all the way down to 100 centimeters. So I'm going to have 50 measurements, 10 measurements here at 20 centimeters, 40, 60, 80, and 100 measurements at 100 centimeters. I'm going to end up with 50 time measurements. If you follow this, the instructions here gives you detailed directions as to how to treat the data. But basically, for each, like at the 20 meter mark, a 20 centimeter mark, we have 10 measurements. You take the average, so you find the average time that it took the ball to roll 20 centimeters. Then you do the same thing for 40 centimeters, and likewise all the way down to 100 centimeters. At this point, we're down to analysis number 4. And what I want you to do is to draw two curves at the same scale, at the same time scale. And draw this on one piece of paper. The first plot will be displacement, which is x, displacement. And that's in centimeters. That's 0. And that will be 100 centimeters. The second graph is velocity. In centimeters per second, from 0 to some number here. From your average time data, what you will do is you'll say, okay, the ball rolled to 20 centimeters in x, whatever the time is, and you're going to plot this point, plot this point, plot this point, plot this point, and you're going to draw a smooth line to this. Now what you should find out is that this is a curved line. As the ball rolls down the ramp, the speed picks up, so the slope increases. It makes sense. Remember, the velocity is the slope of this line. As the ball rolls down, it's going to pick up speed, so the curve, the slope of this will gradually increase. Okay? Now, suppose let's suppose this time measurement is 0.2 seconds, and let's suppose this time measurement here was 0.35 seconds. When we plot velocity, what we're going to do is we're going to plot the average velocity from 0 to 0.2 seconds, but the average velocity doesn't happen in 0.2 seconds. The average velocity happens at the midpoint. So the midpoint is 0.1, and you're going to calculate what the average velocity is from this point to this point. Whatever that average velocity is, you're going to plot it at this midpoint. Hopefully that makes sense. So when you plot the average velocities here, for instance, the average velocity in this realm, in this, here we go. The average velocity plots to the midpoint from here to here. The average velocity from 20 to 40 centimeters plots actually at the midpoint in here. So the velocity points are plotted in the midpoints of the times between these intervals. I hope that makes sense. And then we want you to plot a third graph down here, again, of time versus acceleration. And this should have a constant acceleration, but it may not. When you get to acceleration, again, acceleration is equal to the change in velocity over the change in time. Notice we have these velocity points from here to here. There's a change in velocity from here to here. That change in velocity gets plotted at the midpoint, which is back to here. So that change in velocity is from this calculated velocity to this calculated velocity. It's that change in velocity over the delta t, this change in time from this midpoint to that midpoint. The directions hopefully are clear. If they're not, you can always contact me. Well, this concludes this lecture for Module 1 and a brief introduction to the laboratory. Again, just a reiteration of the lab, when you do your lab report, what I'm looking for is your graph of displacement, velocity, and acceleration to be all on one sheet of paper, just like this is here, at the same time scale for each graph. Hope that's clear. Well, God bless you, and this concludes Module 1, and we will see you next time. So long.